When people talk about CPU performance, they often focus on clock speed, gigahertz, core counts, execution units. But in real systems, one of the biggest performance limits isn't how fast the CPU can compute. It's how long the CPU has to wait for data. That waiting time is called memory latency. In this video, we're going to explain what memory latency is, why it exists, how it affects software execution, how it differs from bandwidth, and why understanding latency is essential for writing high-performance code. Let's start with a simple idea. Latency is the delay between requesting data and receiving it. If the CPU needs a value from memory, it sends a request. Some number of clock cycles later, the data arrives. That delay, measured in cycles or nanoseconds, is memory latency. Now here's the problem. Modern CPUs can execute instructions in a fraction of a nanosecond, but accessing main memory can take tens or even hundreds of nanoseconds. In CPU cycles, that might mean waiting 100, 200, or even more cycles for a single memory access. That's an enormous gap. While waiting, execution units may sit idle. Even with pipelines and out-of-order execution, if there isn't enough independent work available, the processor stalls. This is why memory latency is often more important than raw compute speed. Now let's connect this to the memory hierarchy. In the previous video, we discussed caches. L1 cache might have a latency of a few cycles. L2 might take around 10 cycles. L3 might take several dozen cycles. Main memory might take hundreds. The farther the data is from the CPU, the higher the latency. When you access a memory address, the processor checks the closest cache first. If it finds the data in L1, that's a cache hit, very fast. If it doesn't, it checks L2. If not there, L3. If not there, it must go to RAM. Each step adds delay. This layered system exists to reduce average latency. Most programs rely heavily on locality. If you access data that's already in cache, latency is low. If you access data that isn't, latency spikes. Now let's clarify something important. Latency is not the same as bandwidth. Latency is how long it takes to start receiving data. Bandwidth is how much data can be transferred per unit of time once transfer begins. Imagine ordering something online. Latency is the time between placing the order and receiving the package. Bandwidth is how many packages can be delivered per day. You can have high bandwidth, but still suffer from high latency. In many workloads, latency is the dominant bottleneck. Now let's talk about why latency matters so much for execution. Consider a simple example. You load a value from memory, then you use that value in the next instruction. If the value is not in cache and must be fetched from RAM, the second instruction cannot execute until the data arrives. Even with out-of-order execution, if there are no independent instructions available, the pipeline stalls. This is called a load-to-use latency. The CPU is fast, but it cannot compute without data. Now let's introduce memory-level parallelism. Modern processors try to reduce the impact of latency by issuing multiple memory requests simultaneously. If one load is waiting on RAM, the processor might issue other loads that don't depend on it. If enough independent memory operations exist, the CPU can overlap some of the latency. But this only works if the program structure allows it. If every operation depends on the previous load, latency becomes unavoidable. This is why pointer-heavy data structures, like linked lists, can perform poorly. Each node depends on the previous one. You cannot fetch the next address until you've read the current one. That creates a chain of dependent memory accesses. Each one incurs latency. On the other hand, iterating through an array sequentially allows the CPU to prefetch upcoming data. Prefetching is another technique to hide latency. The processor predicts which memory addresses you will need next and loads them into cache ahead of time. If it guesses correctly, when your program requests the data, it's already there. This reduces perceived latency. Now let's discuss how latency affects algorithm design. Two algorithms with the same number of arithmetic operations can perform very differently depending on memory access patterns. An algorithm that accesses memory sequentially will benefit from spatial locality and prefetching. An algorithm that jumps unpredictably across memory may suffer frequent cache misses and high latency. In modern systems, optimizing memory access patterns can be more important than reducing arithmetic operations. Now let's talk about latency in cycles versus nanoseconds. Latency is often measured in clock cycles because CPUs operate on cycles. If your processor runs at 3 GHz, one cycle is roughly 1/3 of a nanosecond. If main memory latency is 100 nanoseconds, that translates to roughly 300 cycles. That means one memory access can cost as much time as hundreds of arithmetic instructions. This is why we say that memory is the bottleneck. Now let's connect latency to everything we've covered in the series. Superscalar architecture allows multiple instructions per cycle. SIMD processes multiple data elements per instruction. Out-of-order execution rearranges work to keep pipelines full. But all of these mechanisms depend on having data available. If memory latency is too high and cannot be hidden, execution units stall. No amount of compute capability helps if data isn't ready. This is why understanding memory latency is essential for understanding real performance. Now let's address a common misconception. Some people assume that faster RAM eliminates latency problems. While improvements help, the gap between CPU speed and memory speed has persisted for decades. CPU performance has increased faster than memory latency has decreased. This is known as the memory wall. Caches, prefetching, and memory-level parallelism exist to mitigate this gap, but the fundamental latency difference remains. Now let's zoom out. Memory latency is the delay between requesting data and receiving it. It is measured in cycles or nanoseconds. It grows as you move farther from the CPU core, and it can dominate performance in memory-intensive workloads. Understanding latency changes how you think about performance. It shifts focus from pure computation to data movement. It explains why cache-friendly code is faster. It explains why certain data structures scale poorly. And it explains why high-performance systems are designed around locality. If you want to continue deeper into the memory system, the next step could be exploring memory bandwidth, cache coherence in multi-core systems, or virtual memory and the translation look-aside buffer. But for now, you can summarize memory latency like this. Memory latency is the time delay between requesting data and receiving it. And in modern systems, that delay often defines performance more than raw compute speed. Understanding that principle is essential to understanding software execution at a deeper level.